We're asked to find the intervals where the function f of x, 24 divided by x squared plus 12, is concave upward or concave downward. As you've already read, in order to determine concavity, we need to look at the second derivative. So let's start by taking two derivatives of this function. So f prime of x is going to be the derivative of the top, which is 0, times the bottom, which is x squared plus 12, minus the derivative of the bottom, which is 2x, times 24. We're going to divide all of that by the bottom, x squared plus 12 squared. If we clean that up a little bit, we get negative 48x, all divided by x squared plus 12 squared. If we take a second derivative, f double prime of x, we're going to get the derivative of the top, which is negative 48, times the bottom, which is x squared plus 12 squared, minus, we're going to take the derivative of the bottom. By the chain rule, this will be 2 times x squared plus 12 to the first power, times the derivative of what's inside those parentheses, x squared plus 12, which is 2x. Then we multiply all of that by negative 48x. This all gets divided by x squared plus 12 squared, and then we square that again. So we're going to end up with x squared plus 12s in each and every term. So we're going to be able to cancel some of those. So let's see what we get here next. So we have f double prime of x is equal to negative 48 times x squared plus 12 squared minus, we'll multiply everything together except for the x squared plus 12. So we're going to have 2 times 2 is 4. 4 times a negative 48 is 196, but then we have another negative, so we're going to have plus 196 x squared. Let me do that. Actually, I take that back. It's going to be 192 x squared. 2 times 2 is 4. 4 times the 40 is 160. 4 times 8 is 32. 160 plus 8 is 192 x squared. And that's still being multiplied by x squared plus 12. And if we simplify the bottom, we get x squared plus 12 to the fourth power. So here we can cancel one of the x squared plus 12s in the first term on the top, the entire x squared plus 12 to the first power in the second term on the top, and we'll end up with 3 x squared plus 12s in the bottom. So let's see what that gives us. We're going to end up with negative 48 x squared. We're going to have negative 48 times 12. Let's see what that is. I'm going to pull up my calculator here. Negative 48 times 12, negative 576, plus 192x squared, all divided by x squared plus 12 squared. So if we combine the x squareds, we're going to have 192 minus 48. We're going to end up with 144x squareds. Let me go on to a new page here and see if we can add a new page for us. So f double prime of x is equal to 144x squared. Let's go back here for a second. We had minus 576, all divided by x squared plus 12. Now to the third power. Let's make sure I wrote that down right on the previous page. I didn't. I wrote that as the second power. This should have been the third power, just like we see the 3 there from when we did our canceling. All right. So what we're interested are numbers that aren't in the domain of the original function f. We're interested in zeros of the second derivative, and we're interested in places where the second derivative is not defined, but still values that are in the domain of the original function. So the only problem we have with the original function was the fact we have that x squared plus 12 in the bottom, and that can't ever be negative. The smallest that can be is 12. We're always adding a positive number to that because of the x squared. So that goes back to the original function. It has no vertical asymptotes. It's going to be defined everywhere on the real number line from negative infinity to infinity, so no problems there. Same issue with having the second derivative undefined. Since this can't be 0, we don't run into that issue. The only problem we have to consider, if you want to call it a problem, is 144x squared minus 576. Well, let's see if we can divide 576 by 144. And yes, we can. So if we divide out 144, we're going to get x squared minus 4, which leads us to two numbers, plus or minus 2. Once we have those numbers, we set up a sign chart, -2, +2, and those are the only places that we have found where the function can change its concavity. So we'll do some test values, f double prime of -3, f double prime of 0, f double prime of +3. And I'll note once again that the denominator is always going to be positive, so we only need to worry about the sign of the numerator. So if I take 144 times -3 squared and subtract 576, I get a positive number. And if I take 144 times 0 squared and subtract 576, I'm going to get exactly -576. And if I plug 3 in, I'll get a positive number again. So this function is concave up, then concave down, then concave up again. As with when a function was increasing and decreasing, we'll write this out explicitly. So we're concave upward on -infinity to -3 and on 3 to infinity. We are concave downward on -2 to 2. Sorry, I used the wrong numbers there. -infinity to -2, 2 to infinity, -2 to 2. Be careful, what I accidentally did there was include my test values when I was writing where we were concave up and down. I want to use the actual zeros that I got from the second derivative, those things that actually divide my number line up into different chunks. So with that corrected, there is a good final answer to that question.